Hey, it's Bruno here. Just want to say welcome, congratulations on your second day. It seems like the coworkers are impressed with you. They told me that you talked to them about what machine learning is, and they were impressed with your amount of knowledge. So good job. But anyway, we got to get you working because we have a lot of clients and they really need us. So we have a client right now that needs to implement their own machine learning data science framework for their employees. They have about 20 data scientists, 20 machine learning engineers, and everybody's kind of doing their own thing. We need a way to standardize their practices into one so that they can manage all their employees. Would you mind creating a framework that our clients can use and maybe we can use at our company as well? Kaggle Corp needs something standardized so that when we hire more people like you, we're able to have a nice, clear framework that they can use. Shouldn't be a problem for you, right? Genius? All right, there you are. You passed the first day, but second day, we got to create this framework and Bruno wants it done by tomorrow. So what do? Well, it's time to ask your friend Andre and Daniel. So in this section, we're going to build our own machine learning and data science framework. That is a template that we can use throughout the rest of the course, throughout the rest of your career to think about how to solve problems. Here's the thing with this section. This is the last section of the course where we talk about theory and we look at some slides and look at some diagrams. After this section, we go into full coding. We're going to start actually building our own models, actually working with data for the rest of the course. But this section is really, really important because when you go through it the first time, it's not going to stick automatically. This section, we left it this way so that you can come back to it every once in a while throughout your career, also throughout the course, to be reminded of the framework that we're using, of the steps that we're using. And the rest of the course is going to build on this framework and build our skills so that we become better and better with this framework. But like I said, it's not going to stick right away. So every once in a while, if you feel a little bit overwhelmed throughout the course, or maybe you're not getting something, maybe hit pause and come back to this section and rewatch it. And at the very end of the course, when you've finished all the lectures, I want you to come back to this section and realize how much you've learned, how much clearer this framework becomes once you've completed the course. And like I said, this is going to be the last section where we're just talking without you actually getting to practice and code. But once we build this, we're ready to dive deep. So let's get started. Let's create our own framework and hopefully go into work the next day and make Bruno happy once again. Survive day 2. Let's get started.
Now, if you've looked up machine learning before, you know there's a lot out there. Some resources recommend learning mathematics, statistics, probability, and even more before getting started with data science and machine learning. And while these topics, they're important, trying to learn them all before getting started, getting hands-on, is like trying to boil the ocean. Instead, what we're going to be doing is focusing on building practical solutions and writing machine learning code to get insights out of data. If you're a programmer now and had some experience with Python, by the end of this course, you'll be able to use your programming skills to build predictive machine learning models. Machine learning comes in 3 parts: data collection, data modeling, and deployment, where you might take your machine learning model after you've gone through these steps here. Don't worry, we're going to cover this framework in depth shortly. You might take this machine learning model and deploy it to users through your application or through an API or some sort. This is what we're going to cover. We're going to cover data modeling, which means you'll be able to take a data set and apply machine learning algorithms to find insights on that data set. The steps we're going to cover is number 1, create a framework. You saw a little bit of an outline of that in the previous slide. Number 2, we're going to match that framework once we've gone through it to available data science and machine learning tools. This means that people have already had similar problems to what we're going to try and solve in the future in the past, and so they've created tools for those problems. So we're going to learn what tools are used for what machine learning projects. And then to learn all of this, we're going to learn by doing, by going through projects which involve step 1 and step 2 to build a portfolio to show off your work and your skills. The utmost care has been taken to focus on what matters. When I started learning machine learning, I found myself confused about what to do. Too often I'd spend too much time thinking about something instead of writing code and taking action. So we've designed this course to avoid that. Instead of doing anything and everything from scratch, we're going to be using what works to build practical solutions and at the same time learning about machine learning and data science. Now, let's take a deeper look at the framework we're going to be using. Since machine learning projects can cover many different topics, it's important to design a framework you can use to approach different kinds of problems. You can consider what we're about to go through as like a little field guide that you can use for machine learning. So when you come up against a problem, you can refer back to this field guide and go, hold on, I need to break this problem down into a few little steps. What does the field guide say? The framework we're going to be using comprises 6 steps. After working on many machine learning projects across multiple different industries, these are the steps I've found which come up time and time again. We're going to see this diagram a lot in the next few lectures, but in this one we're going to dive into each of these steps individually and see what kind of components they have. Step 1 is problem definition. Since we'll be focused on code first, practical solutions, it's important to define what problem we're trying to solve. Is it a supervised or unsupervised learning problem? Is it a classification or regression problem? Don't worry, we'll see how to figure these out in the next few lectures. Step 2 is data. Since machine learning involves using algorithms to find and learn different patterns in data, data is a requirement for any machine learning project. The question we're trying to answer here in step 2 is what kind of data do we have? Depending on the problem, there are different kinds of data. Structured data, such as rows and columns, or what you'd expect to find in an Excel spreadsheet. Or unstructured data, such as images or audio. Once we know what kind of data we have, we can start to make decisions on how to use machine learning with it. Step 3 is evaluation. Here, we'll define what success means to us. Since much of machine learning actually is experimental, you could keep going forever trying to improve your results in search of the perfect model. However, since we're practitioners, we know the perfect model doesn't exist. Instead, we begin by saying, for this machine learning real estate project to be feasible, we need at least a 95% accurate model at predicting the cost of houses. Of course, in the beginning, this evaluation metric won't be exact and will likely change over time, but having this at the start of a project gives us something to aim for. Step 4 is features. The question we answer here is, what do we already know about the data? Now, even within different types of data, there are different kinds of features. For example, for predicting whether or not someone has heart disease, you might use their body weight as a feature. Since body weight is a number, it's called a numerical feature. And after talking to a doctor, they might tell you if someone's body weight is over a certain number, they're more likely to have heart disease. There are more kinds of features such as categorical and derived. We're going to look at these in future lessons. But the premise remains. A machine learning algorithm's goal is to turn these features, such as weight, sex, blood pressure, and chest pain, into patterns to make predictions, such as whether or not a patient, we've got unique patient IDs here, has heart disease or not. Step 5 is modeling. Once you've learned a little bit about your data, the next step is to model it. And the question here is, based on our problem and data, what machine learning model should we use? Unlike other algorithms and sets of instructions you have to write from scratch, many of the most useful machine learning algorithms have already been coded for you, which is beautiful for us. Some models work better on different problems than others, And in the beginning, your focus will be to figure out the right model for the right kind of problem. Step 6 is experimentation. All of the steps we've just been through happen in a cycle. You might start out with one problem definition and find your data isn't suited to it. Then you might build a model and find it doesn't work as well as you outlined in your evaluation metric. So you build another one and you find out this one actually works pretty good. But what's important to remember is although these steps are here, those steps that we've been through in this framework, it doesn't mean that they have to be followed in order, nor are they set in stone. Consider them a rough guide. Now we've been through each of them briefly, let's look at each one in a little bit more detail. Look at this beautiful framework. Now we've covered each of these steps briefly. We're gonna dive into each of them one by one. The first one is problem definition. The question you're trying to answer in the first step is, what problem are we trying to solve? But before we get into different types of machine learning problems, it's important to note, machine learning isn't the solution to every problem. You might think that that's weird being in a machine learning course, but this is an important concept to remember. So when shouldn't you use machine learning? Well, will a simple hand-coded instruction-based system work? Then you should favor the simpler system over the machine learning system. Such as if you wanted to make the favorite chicken dish we used before in the example, if you had the ingredients and you knew the exact steps you had to take to create your favorite chicken dish, it's probably best that you choose a simple system over using machine learning to try and figure the steps out. Other than these kind of scenarios where you know the simple hand-coded instruction-based system already, most of the time you can probably find value using machine learning. Now comes the first step in identifying the problem we're trying to solve as a machine learning problem. We can do this by matching our problem, the one we're working on, it might be a business problem or some other kind of problem, to the main types of machine learning problem. These are supervised learning, unsupervised learning, transfer learning, and reinforcement learning. We're going to be focused on supervised learning, unsupervised learning, and transfer learning. Why? Because these are the most common ones you'll find and you'll come across in practice. And they're the ones when I was a machine learning engineer or when I work on machine learning problems that have proven time and time again to be useful. Supervised learning is called supervised learning because you have data and labels. A machine learning algorithm tries to use the data to predict a label. If it guesses the label wrong, the algorithm corrects itself and tries again. This act of correction is why it's called supervised. It's like if you were trying to guess the steps it took to turn a set of ingredients, the data, into your favorite chicken dish, the label. If you tried once and got it wrong, you'd tell yourself, this was wrong. Maybe next time we'll try something different. A supervised learning algorithm repeats this process over and over and over again, trying to get better. The main types of supervised learning problems are classification and regression. Classification involves predicting if something is one thing or another, such as if you wanted to predict whether or not a patient had heart disease or not based on their medical records, or what type of dog breed was in an image. If there are only two options, it's called binary classification. If there are more than two options, it's called multi-class classification. So trying to predict heart disease or not heart disease would be binary classification because there's only two classes, heart disease or not heart disease. And trying to predict different dog breeds based on photos in images would be multi-class classification because there are many different kinds of dog breeds. Regression problems involve trying to predict a number. You might hear it referred to as a continuous number as well, which just means a number which can go up or down. A classical regression problem is trying to predict the sale price of a house based on things like number of rooms, the area it's in, how many bathrooms it has, or trying to predict how many people will buy a new app based on website visits and clicks. Unsupervised learning has data but no labels. For example, you might have the purchase history of all customers at your store, and your marketing team wants to send out a promotion for next summer. But they know not everyone will be interested in new summer clothes. So they come to you as the in-house data science and machine learning engineer and ask, do you know who's interested in summer clothes? Well, the thing is, you don't either, but you know you can figure it out from the data you have. So you decide to run an algorithm to find patterns in the data and group customers who purchase similar things together. Once it's finished, you notice two groups. One group of customers who purchase only during wintertime, and one group of customers who purchase mostly during summertime. You label them with winter customers and summer customers and send them to your marketing team. And they thank you for saving them sending out thousands of unwanted emails. I'm sure you've probably got some of those kind of emails in your email inbox before. What's important to note here is that you provided the labels. They weren't there to begin with, but the patterns were. And that's what the machine learning algorithm found. And after inspecting the groups, you're the one who saw the commonalities and applied the labels, such as summer or winter. Problems like this are also called clustering, or putting groups of similar examples together. Recommendation problems such as recommending what music someone should listen to based on their previous music choices often start out as unsupervised learning problems like this. Transfer learning leverages what one machine learning model has learned in another machine learning. For example, say you're trying to predict what dog breed appears in a photo. That's a cute dog. That's my Papi 7. And that's Bella in the background there. She's posing. She knows she's on this lecture. You could find an existing model which has learned to decipher different car types and fine-tune it for your task. Now, why is this valuable? Because training a machine learning algorithm, which means letting it find all of the patterns in data, can be a very expensive task. To find patterns in data, a machine learning algorithm has to make millions of calculations. And although computers are very fast at making calculations aren't free. So, instead of learning everything about different photos from scratch, such as what patterns different trees look like, what different shapes are, like the rectangle down here, what grass looks like, the car type model, the machine learning model which has figured out what kind of different cars look like, has already done most of these things. If you've already trained a model, it might have already figured out, okay, these are trees, not cars, these are grass. And so it kind of has an idea of what different patterns look like. Now, you can think of this as being the same as when you write an essay versus writing poetry. Although the writing styles are different, the writing that you do uses the same fundamental principles. So, we can take this car model that it identifies different cars and use its foundational patterns and apply it to our dog breed problem. Of course, there's a few more steps involved here, but that's the basic premise of transfer learning. Reinforcement learning involves having a computer program perform some actions within a defined space and rewarding it for doing it well, or punishing it for doing poorly. A good example is teaching a machine learning algorithm to play chess. The chessboard is the defined space, and the actions are moving pieces. And when I say punishment or reward, these things could be as simple as updating a score with +1 if it wins, and -1 if it loses. The machine learning's algorithm's goal could be to maximize the score. So this means if you've done it right, it should learn moves which lead to wins. Reinforcement learning is what was used for DeepMind's AlphaGo to become the best Go, a complicated Chinese board game, far more complicated than chess, player of all time, defeating many Go world champions. And although promising, reinforcement learning has yet to find its way into many practical applications. And since we're focused on building practical solutions, we've decided to focus on the other kinds of learning, such as supervised learning, unsupervised learning, and transfer learning throughout this course. Now you know the major types of learning, you've now got the tools to tackle step 1 in the framework, problem definition, aligning the problem you're trying to solve to a machine learning problem. So for supervised learning, you might say, I know my inputs and outputs, such as I've got patient records, could be the inputs, and the outputs are whether or not the patient has heart disease. Or your inputs could be the parameters of a different house, and the number of rooms, where it's located, how many bathrooms there are, and your outputs are how much the house costs. So that's a regression problem. And for unsupervised learning, you might say, I'm not sure of the outputs, but I do have inputs, such as customer purchases. And you're trying to figure out which customers are most similar to each other. Or for transfer learning, you may think, my problem might be similar to something else. Can I leverage what an existing machine learning model has learned and use it in my own? Now, don't worry if these kinds of learning are sort of going over your head at the moment. We're going to be building a hands-on project for each of these learning types, supervised, unsupervised, and transfer, throughout the course. In the meantime, have a think about some of the problems you face day to day. Could any of them be classified as a machine learning problem? Are you trying to classify whether one thing is something or another? That's a classification problem. Do you ever try to predict what a number might be? That could be a regression problem. Now we've figured out what problem we're trying to solve, we've matched our specific problem to a different type of machine learning problem, it's time to have a look at what data we have. As you may have guessed, the question we're trying to answer here is, what kind of data do we have? Data comes in many different shapes and sizes, but the main two types are structured and unstructured. Structured data is something you'd expect to see in an Excel file, such as rows and columns of different patient medical records, and whether or not they have heart disease or not. Or customer purchase transactions. It's called structured data because all of the samples, the different patient records, are typically in similar format, meaning one column might contain numbers of a certain type, such as average blood pressure, or sex, or weight of a patient, and another column might have whether they have chest pain or not and what the level of intensity is. Unstructured data are things like images, natural language text, such as transcribed phone calls, videos, and audio files. Although we can turn these into numbers and create structure, they typically come in many varying formats. One picture of a dog may look completely different to another image of a dog. And the emails you write back and forth with a friend may have a completely different structure to the emails you'd write to a coworker. Now within these two data types, there's static and streaming data. Static data is data which doesn't change over time. You may have a spreadsheet of patient records in a .csv format, which stands for comma-separated values, which simply means all of the different data is in one file, separated by commas. It looks like this. So you check this table, we've got the ID, comma, weight, comma, sex, and if we were to read that into a data frame using a tool like Pandas, we'll have a look at this in a future lesson, it would look something like this. So a lot of data you'll actually come across comes in a simple format like this, but to turn it into something that is a little bit more structural, you can convert it to this. Now CSV is one of the most common types of static data formats. We're going to get very used to this by the end of the course. And since these values won't really change over time, they're called static. Usually, what you'll want is a lot of these examples. In machine learning, there's a saying, the more data, the better, which makes sense if you think about it. The more examples you have of something, such as the inputs and outputs of patient records, where the inputs are a patient's body parameters and the outputs are whether they have heart disease or not, the more chances you'll have to find patterns between them. The same goes for machine learning algorithms. The more examples they can look at, the more chance they have at finding patterns, and thus using those patterns to predict something in the future, like whether a new patient who comes along who isn't in this table, whether they have heart disease or not. Streaming data is data which is constantly changed over time. For example, say you wanted to predict how a stock price will change based on news headlines. You'd be working with streaming data. Since news headlines are being updated constantly, you'll want to be the first to see how they change stocks. Most of the work you will do in practice will start on static data, and then if your data analysis and machine learning efforts prove to show some insights, you'll move towards streaming data for when you go to deployment or in production. A common data science workflow begins by opening a CSV file in a Jupyter notebook, a tool for building machine learning projects, then exploring the data and performing data analysis using Pandas, a Python library for data analysis, and making visualizations such as graphs and comparing different data points using MatPlotLib, then building machine learning models on the data using Scikit-Learn, such as a machine learning model to predict, using these patterns here, whether or not a patient has heart disease. Don't worry if you're thinking, what's a Jupyter notebook and pandas? What? Are we at the zoo? We've got dedicated sections and projects coming up for each of these tools. For now, think about the different kinds of data you create or use every day. Are they structured or unstructured? How much data is there? Now we've gone through step 1 and 2, problem definition and data. It's time for step 3, evaluation. Now, every machine learning problem you come across will have the similar goal of finding insights in data to predict the future in some way. An evaluation metric is a measure of how well a machine learning algorithm predicts the future. And in this step, the question you'll want to answer is, what defines success for us? For example, if your problem is to use patient medical records to classify whether someone has heart disease or not, you might start by saying, for this project to be valuable, we need a machine learning model with over 99% accuracy. Because predicting whether or not a patient has heart disease is an important task, so you'll want a highly accurate model. And as you could imagine, there are different evaluation metrics for different problems. For classification or predicting whether something is one thing or another, accuracy, precision, and recall are common. For regression or predicting a number, such as how much a car will sell for, you'll probably want to minimize how different the number your model predicts to the actual sale price. For this, mean absolute error and mean squared error are common options. Or for recommendation problems, you may have thousands of different products to recommend to someone, but in reality, you only care about the top 10 recommendations and how well they align to a customer's potential interest. To measure this, you could use precision at K, where in our case, K is 10. Sitting down and thinking about an evaluation metric at the start of a project ensures everyone on it has a similar goal to work towards. But it's important to remember, these don't have to be exact either. As you find out more about the data, you might find the evaluation metric changes as the project goes on. For now, don't worry if you're not too sure about each of these. We'll see different examples of these as we build projects. As an example of an evaluation metric being used in practice, we had a project where we wanted to use the text from car insurance claims to predict who caused the accident. The person submitting the claim or the other person involved. The car insurance company we partnered with wanted at least a 95% accurate model to consider the project worth continuing. This meant the model I was building had to be able to read a car insurance claim and predict with 95% accuracy who caused the accident. This meant it was only allowed to get it wrong 1 out of 20 claims. Again, we'll learn more about evaluation metrics when we get hands-on for different projects. But the thing to remember is, as you go, you'll start to define a problem like in step 1. Then you'll start to remember, oh, this is a classification problem. I should use accuracy as my evaluation metric to get an idea of how my model is doing. Before we go on to step 4, have a think about different things you measure every day. How do you measure them? Are there different kinds of measurements for different tasks? We've gone through step 1, problem definition. We've gone through step 2, data. And step 3, we've defined what success means for us. Now let's get on to step 4, which is features. Now here the question we're trying to answer is, what do we already know about the data? Now if you haven't worked with data before, you might hear this word features and be wondering, what the hell does features mean? Well, you'll hear this word come up a lot in machine learning. Maybe in the form of feature learning or feature variables, or when someone asks, how many features are there? Or what kind of features are there? Features is another word for different forms of data. Now, we've already discussed different kinds of data such as structured and unstructured, but features refers to the different forms of data within structured or unstructured data. For example, let's go back to our predicting heart disease problem. We might want to see if things such as a person's body weight, their sex, their average resting heart rate, and their chest pain rating can be used to predict if they have heart disease or not. These three things, a patient's body weight, sex, average resting heart rate, and chest pain, are features of the data. They could also be referred to as feature variables. In other words, we want to use the feature variables to predict the target variables, which is whether or not a person has heart disease or not. Now, when it comes to feature variables, again, there are different kinds. You've got numerical, which means a number like body weight. There's categorical, which means one thing or another, like sex, or whether a patient is a smoker or not. And then there's derived, which is when someone like yourself looks at the data and creates a new feature using the existing ones. For example, you might look at someone's hospital visit history timestamps, and if they've had a visit in the last year, you could make a categorical feature called visited in last year. If someone had visited in the last year, they would get true, or in our case, yes. If not, they would get false, or in this case, no. The process of deriving features like this out of data is often referred to as feature engineering. Our heart disease example is structured, but unstructured data has features too. They're just a little less obvious. If you looked at enough images of dogs, you'd start to figure out, okay, most of these creatures have four shapes coming out of their body. Their legs and a couple of circles up the front. Their eyes. As a machine learning algorithm looks at different images, it would start to learn these different shapes and much more, and figure out how different pictures are similar or different to each other. Don't worry, when it comes to figuring out the different patterns between features, such as the four rectangle sort of shapes coming out of a dog's body or the circles at the front of the dog's head, you don't have to tell the machine learning algorithm what they are. The beautiful thing is, it figures them out on its own. The final thing to remember is, a feature works best within a machine learning algorithm if many of the samples have it. For our predicting heart disease problem, say we had a feature which was called most eaten foods, which had a list of the foods the patient ate most often. But only 10% or 10 out of 100 patient records had it. So this one, patient ID 4328, has most eaten food, which is fries. Not ideal. And these other patients don't have it because, remember, only 10 out of 100 examples have the most eaten food. They have data here, so these ones are just missing. And that'll be the same. So if you can imagine there's 100 patients here, only 10 of them will have this most eaten food column filled. And since a machine learning algorithm learns best when all samples have similar information, we'd either leave this one out or try to collect more information before using it. The process of ensuring all samples have similar information is called feature coverage. In an ideal dataset, you've got complete feature coverage. So for us to want to be able to use this feature of most eaten foods, ideally we'd want all values here, or at least more than 10% coverage, which means that over 10% or over 10 in 100 examples have some sort of value in this column. We'll have plenty of practice looking at different features in coming lectures and projects and lessons. In the meantime, think about a problem you had to solve recently. What features went into it? Were they numerical or categorical? Or did you combine them into your own derived feature? Look at us go! We're moving through this framework at lightning pace. We've done problem definition, we've looked at data, we've decided on an evaluation metric, we've understood a few of the features we've got in our data. Now we're up to step 5, which is modeling. Now, there's a few parts to modeling, so we've broken this down into 4 different sections. And we're in section 1. And this is probably the most important concept in machine learning, the 3 sets. And now, over the whole of modeling, we want to answer the question, based on our problem and data, what machine learning model should we use? Modeling can be broken down into 3 parts: choosing and training a model, tuning a model, and model comparison. Before we get into these though, part 1 of modeling is, and the most paramount topic to discuss in this whole entire course, is the most important concept in machine learning: the train, validation, and test splits, or commonly referred to as 3 sets. Now, since you want to be using machine learning models to gain insights on some data to predict the future, it's important to test how well they would go and do in the real world. To do this, you split your data into 3 different sets: a training set to train your model on, a validation set to tune your model on, and a test set to test and compare your different models. Why is this important? Think of it like this. When you're at university, you might study the course materials all through the semester. Then, before the final exam, you might see how you can improve your knowledge on a practice exam. After doing well on the practice exam, you're confident you'll do well on the final exam. You take the final exam, and although some of the problems you've never seen before, you're able to adapt the knowledge you've learned from the study materials to the slightly different but similar questions on the final exam. Because of this, you pass the final exam with great marks. This adaptation that you had from the course materials and practice exams to the final exam is referred to in machine learning as generalization, or the ability for a machine learning model to perform well on data it hasn't seen before because of what it's learned on another data set. Now, where might this go wrong? Well, if your professor accidentally sent out the final exam for everyone to practice on, when it came time to the actual exam, everyone would have already seen it. Now, since people know what they should be expecting, they go through the exam, they answer all the questions with ease, and everyone ends up getting top marks. Now, top marks might appear good, but did the students really learn anything? Or were they just expert memorization machines? For your machine learning models to be valuable at predicting something in the future on unseen data, you'll want to avoid them becoming memorization machines. This is where training, validation, and test splits come in. In our heart disease example, let's say there were 100 patients. We start off with 100. One way to create these splits is to shuffle these patients, then select 70% for training, which would mean that would be about 70 patient records there, and 15% for validation, and 15% for testing, which means there'd be 70 patients in the training set, 15 patients in the validation split, and 15 patients in the test split. Now, the percentages of each of these may vary, but standard practice is usually around 70 to 80% for training, 10 to 15 for validation, and 10 to 15 for test. You may see in some examples that some sets or some data sets only get split into training and test, but that's case by case scenario. Usually you'll have 3 different sets. Then, once you've got these splits, using a model you've chosen, you'd feed it the training data or the information of these 70 patient records. And once your model had trained, you can check its results and see if you can improve them on the validation set. This is where you'll do model tuning. So just because your machine learning model's got one set of results on the patient records, you can actually improve them, and we'll see this in a future lesson, on the validation split. Well, the validation split is where you should be testing to see if you can improve it. And finally, once you've improved your model, you can check the model's results as well as any other model's results that you might have done during experimentation on the test set. What's important to remember is that all three of these sets are separate. During training, the model never sees a validation split or the test split. And during testing, you're doing it on the test split, not the training set. It's the same as when you were studying for your exam. If you saw the final exam whilst practicing, that would be cheating, and your final result wouldn't reflect how well you'd learned. For now, think about the last time you went for a test. Did you practice beforehand? Was the practice you were doing helpful for the test? And when you're thinking about this, try and think of how it aligns to why it's important to not let a machine learning model see a test set or a test data split whilst it's training. Step 5, modeling part 2, choosing. We mentioned in the last lesson there were 3 parts to modeling: choosing a model, tuning a model, and comparing models. Once you've got your data split into training, validation, and test sets, you can start to go through each of these steps. In this lesson, we're going to cover some points on choosing a model, which is you choose a model and train it on your training data. Unlike creating your own algorithms from scratch, there are many pre-built machine learning models, which you can take advantage of. When you first begin, your main goal will be knowing what kind of machine learning algorithm to use with what kind of problem. This is because some algorithms work better than others on different types of data. We'll have a look at this specifically when we get hands-on with our projects. But for now, a tidbit to remember is if you're working with structured data, decision trees such as random forest and gradient boosting algorithms like CatBoost and XGBoost tend to work best. And if you're working with unstructured data, deep learning, neural networks, and transfer learning tend to work best. Once you've chosen a model, your next step is to train it. The main goal here will be to line up the inputs and outputs. For example, in our heart disease problem, we want our model to look at the feature variables, the inputs, and then find the patterns and use them to predict the target variable. So remember from a previous lesson, these variables here are the feature variables. We want to use these to predict the target variables. Another common naming setting is to use X, which is the data, to predict Y, which is the labels. Different machine learning algorithms have different ways of doing this. We'll see how to do it for a handful of useful ones in future projects. And remember, training a model takes place on the training data split. This is where your model learns the course material. We don't want to let our models cheat and see the final exam before they do their study. Depending on how much data you have and how complex your model is, training may take a while. One of your biggest goals when training a model is to minimize the times between experiments. So, sometimes this will mean to use a small portion of your data first. For example, if your training data set had 100,000 examples, you might start training a model with only the first 10,000 and see how it goes. You might also decide to use a less complicated model to begin with. Deep models such as neural networks generally take longer to train than other kinds of models. Now, this is something worth considering when it comes to training your own models. For example, if an experiment takes you 3 hours or even up to a couple of days for a small percentage boost in performance of your model, you might consider, is this experiment actually worth it? Because machine learning is highly iterative, we want to minimize this experimentation time that we can go from step 1 to step 2 to step 3. But again, if this looks confusing, we'll see it in practice in the hands-on projects. The things to remember. Some models work better than others in different problems. Don't be afraid to try things. Now, this is really important. Machine learning is, as we said before, a highly iterative process. So Some things that you try out may not work the first time, and that means you just neglect that thing going forward and try something else. Start small and build up. Add complexity as you need. What this means is, for example, if you had 100,000 examples, we're going to start on 10,000. We're going to use a simple model first to begin with rather than going to the biggest and latest and greatest model, because what we're after is practical results, not something that's the best on paper. We want to see something that can actually be used in the real world. And part of your experiments will involve tuning a model, which shows good initial results to get better results, like tuning a car. If your car does well on one track, it might not do well on another track, so you tune it up. Let's have a look at how to do that. But instead of for cars, we'll do it for machine learning models. All right. Modeling part 3, tuning. Once you're happy with your model's initial performance on your training dataset, the next step is to try and improve it. Like what we said in the last lesson, how a car can be tuned for different styles of driving, a model can be tuned for different types of data, specifically your data. Usually, this tuning will take place on a validation data split. However, if you don't have access to a validation set due to how you've done your training, validation, and test data split, it can also happen on the training data. Well, many models have different hyperparameters which can be adjusted. You can think of these as the same as dials on an oven. For example, when you're learning to cook your favorite chicken dish, that delicious sweet honey mustard dish. I'm getting hungry making these lectures. You notice that cooking it at 180 degrees for an hour meant it came out a little raw. Not ideal, right? We want this chicken to be nice and crispy. But at 200 degrees, that's when we get the glory. That's 200 degrees for an hour, the chicken came out just right. So like a little dial here, right? This is how you can tune your oven. You can change it from 180 degrees to be 200 degrees. If you leave it on 180 degrees, chicken doesn't turn out well. If you take it up to 200 degrees, chicken does turn out well. Depending on what kind of model you're using will depend on what kind of hyperparameters you can tune. For example, a random forest will allow you to adjust the number of trees. In this one, we've got 3 trees. In this one, we've got 5 trees. Don't worry, we'll have a look at the random forest. This is a type of machine learning algorithm. We'll check this out in a future lesson. And a neural network will allow you to adjust the number of layers. Again, we'll look at a neural network in a future lesson. I'm just giving an example of different hyperparameters like the temperature on an oven you can adjust on different kinds of algorithms. The main things for you to remember are machine learning models have hyperparameters you can adjust. However, depending on what model you're going to use, the hyperparameters will be different. The goal of tuning hyperparameters is to improve your model's performance, and you should do model tuning on your training and/or validation sets. Meaning you train a model using an initial set of hyperparameters. These might be the defaults. Like say, for example, you put your chicken ingredients in the oven, you press roast chicken on the oven, and it goes for an hour on the oven's default settings. And then you find it doesn't turn out how you want it to be. You might adjust them as you go. This is exactly what you'll do with a machine learning model. You might try a machine learning model with an initial set of hyperparameters, the defaults. And it turns out it does okay, but not exactly how you want it. So you might try and improve it by adjusting some of the hyperparameters. Up next, we've got model comparison. Now this happens during your experimentation. Say you've trained multiple different models on the same data set. We're going to look at how you might compare those. And this is done on the test data. So let's do it. Modeling part 4. This is the final part of modeling, and it's comparison. What we're wanting to know here is how will our model perform in the real world? So after you've tuned and improved your model's performance through hyperparameter tuning, it's time to see how it performs on the test set. The test set is like the final exam for machine learning models. If you've created your data splits correctly, it should give you an indication on how your model will perform once deployed in production. That means customer facing rather than just being on your local computer. Since your model has never seen data in the test set, evaluating your model on it is a good way to see how it generalizes. And remember, by generalizing, I mean adapts to data it hasn't seen before, such as how our heart disease prediction machine learning model would perform at classifying whether a patient has heart disease or not on a patient who wasn't in our original data set. A good model will yield similar results on the training, validation, and test sets. And it's not uncommon to see a slight decline in performance from the model on the training and validation set to the test set. For example, your model might achieve 98% accuracy on the training dataset and 96% accuracy on the test set. What you should be worried about is if the training set performance is dramatically higher than the test set, also known as underfitting, and if the test set performance is higher than the training set performance, also known as overfitting. Overfitting and underfitting are both examples of a model not being able to generalize well, which is what we don't want. The ideal model shows up in the Goldilocks zone. It fits just right. Not too well, but not too poorly. You see here, this machine learning model, if this was your data, these green data points, this line here, it kind of fits the shape, but this would be classified as underfitting. This is not what we want our model to do. And this one over here, well, it's doing a good job of fitting all the data points, but it's going far too close. It's almost a too perfect model. It's just snaking between them. So this example would mean that the model has learned the patterns too well in this data set. It would be like seeing the final exam before actually taking the final exam. This one here is the Goldilocks zone, right? This is an iterative process. Where exactly this Goldilocks zone is, like a balanced model, will really depend on your data and the problem you're trying to solve. That's why, again, it's an iterative process, finding this balanced zone. And now after some experience and practice working on different machine learning problems, you'll be able to start to tell whether your model is overfitting or underfitting. Now, there are several reasons why underfitting and overfitting can happen, but the main ones are data leakage and data mismatch. Data leakage happens when some of your test data leaks into your training data. And this often results in overfitting or a model doing better on the test set than on the training data set. It's like, remember, it was like if you were to have a look at the final exam, or everyone had a look at the final exam as the practice exam, your machine learning model has just learned what it's about to be tested on. So when it comes time to modeling, it's just learned it way too well and it starts to fit the data like this. Now this is why it's important to do your splits correctly and ensure that machine learning model training happens only on the training data set. Validation and model tuning happens only on the validation or training data set, and that testing and model comparison happens on the test data set. And remember, some different approaches use only a training and testing set and do model tuning on the training set, but testing always stays the same. It's like when you go to university, you're doing a course, you want to make sure that the final exam is kind of an indication of how well you understand things. Same with the test data set for machine learning. The test data set is used as an indication of how well your model will generalize in the real world, so you want to avoid data leakage. Data mismatch happens when the data you're testing on is different to the data you're training on, such as having different features in the training data to the test data. Having this kind of mismatch can lead to models performing poorly on test data compared to training data. This is why it's important to ensure that training is done on the same kind of data as you'll be testing on, and as close as possible to what you'll be using in your future applications. Other ways to combat underfitting include using a more advanced model. This could mean a totally different model or increasing the number of hyperparameters on your current model. Remember, when we're cooking our chicken dish, we might alter one of the hyperparameters of our oven by turning it up. That might be something that you might do on a machine learning model. Instead of only using 2 layers in a neural network, you might use 4. We'll see more of this in a future project. You could also reduce the number of features you're trying to model. Maybe your data has too many features and the model you're using is struggling to find patterns in them. Finally, you could train your model for longer. Sometimes models take longer to train or longer to learn than you'd expect. One of your experiments may involve a longer training phase. And to reduce overfitting, useful solutions are to collect more data. More data will provide more potential patterns for a model to find and thus lower the potential for it to find them all. Or you could try use a less advanced model. This is uncommon, but it's a possibility the model you're using is too good at learning and it models your data too well. Be cautious of models performing too well, as they might lead to incorrect predictions. Remember, no model is perfect, so be sure to check your good results as much as you check your poor results. Finally, when comparing two different models to each other, it's important to ensure you're comparing apples with apples and oranges with oranges. For example, Model 2 trained on dataset 1 versus Model 3 trained on dataset 1. During comparison, you'll want to make sure you take into account not only the final result, but what it took to get there. If Model 2 takes 1 second to make a prediction at 93.1% accuracy, Model 3 takes 4 seconds to make a prediction at 94.7% accuracy, is that extra 3% accuracy worth that extra 3 seconds of prediction time? Now, this will depend on what the goal is. But if you are optimizing for prediction time, right, you want to make predictions as fast as possible, you might choose Model 2 because it makes predictions 4 times faster than Model 3, but at a higher accuracy level. Again, this will be different depending on what kind of application or production use case you want to use, but just some things to keep in mind. There's more than just how a model performs that goes into choosing which one you should use. A couple of things you want to remember from this lesson. Avoid overfitting and underfitting. You want a model that heads towards generality. It's like when you do your practice exam. If you saw the final exam, you might just become an expert memorization machine rather than someone who could use their knowledge in the real world. Keep the test set separate at all costs. When you split your data, you want to have a training set and then throw away the test data set and lock it up. And once your model has been trained, then you can open up the test data set, you can unlock it, take it out of the safe, and see how your model performs. When you're comparing models, compare apples to apples. Have Model 1 and Model 2 on dataset 1 and dataset 1. You want to make sure the two models you're comparing have been created in the same sort of environment so that you can ensure that what you're comparing is legitimate comparisons. Finally, one best performance metric does not equal the best model. Remember in our example, you may be optimizing for prediction time. So although a model that makes a faster prediction doesn't get as high accuracy as another model that takes a little bit longer, it might not matter to you because you need something that can predict as fast as possible. Phew, that was a lot, but we'll see plenty more of this in action throughout the course. You'll also be using it throughout your entire machine learning career, so it's important to remember these concepts. Let's push on to the next step and see how we can put all of the previous steps together in step 6, experimentation. Y'all ready for this? We got step 6, which is experimentation. And it's important to remember, all of these steps here are a highly iterative process, meaning you might try one thing, find out it doesn't work, then try another, and another, and another, and just keep going through this loop, right? But how would all of this look in practice? Well, with a process like the one we've got here, machine learning projects become tool matching projects. And that's what we're going to do. We're going to use this process and learn the different tools for each step. So eventually you'll be able to start to look at a machine learning problem and think about, okay, I know what tools I can use for each of this step. We can break it down. I can use this for that, that for that, and apply this process to whatever kind of problem you're working on. For example, someone might come to you with a data set and ask you to find insights on it. You might start by defining a problem with them, which is step 1. Then you'll go through to step 2 and look at the data. This part is called data analysis. Here, you might define an evaluation metric based on the problem at the same time as inspecting the different features of the data, which is step 3 and step 4. And once you know a little bit more about the data, you decide to build a machine learning model using the features you found to predict some target. Now this is step 5. Now your first model goes pretty well. We got the little green tick here. You've managed to line up the inputs. You've got a good model. You've matched the model to the problem, and it's producing some good outputs. So you decide to report what you found. And after your initial report, your project manager asks to see if the model can be improved to get better results. So you do your research and find there's another approach you can take. This is step 6, experimenting. You might try a different model. We've got model 2 and see how it goes, and it performs pretty well. Then if that didn't work when you reported it and it's like, oh, maybe you could do a little bit better, you might vary the inputs slightly and change your desired outputs and try a new model. Again, don't worry if all of this looks confusing. We're going to have plenty of practice doing this with hands-on projects throughout the course. Remember at the start how we said there were 3 major steps we were going to do? 1, create a framework. 2, match the framework to data science and machine learning tools. And 3, learn by doing. Well, after going through the last couple of lectures, you've just ticked off step 1. We've now got a framework to use for the modeling section of machine learning projects. Look how beautiful that is. All right, we've got step 1, problem definition. Step 2, data. Step 3, evaluation. Step 4, features. Step 5, modeling. Step 6, experimentation. All of this is an iterative process. Next up, we're going to learn what tools we can use to apply the framework to different projects. And of course, to do all this, we're going to be working hands-on, writing machine learning code and creating projects of our own. Now remember to check the resources section for anything extra you may need. You can find all of what we've talked about there. All right, now I know in the last lecture we said we're gonna jump into different tools, but I thought before we get into the next section, I just want to really highlight that all the steps in this process won't be possible without the right tools. Now there'll be a detailed section on each of these, but as a little sneaky preview, let's have a look at what we'll be using. The first thing is getting your computer set up and ready to use tools that can be used for these different steps. Think of it as creating a work shed for data science and machine learning projects on your actual computer. To do this, we'll use Anaconda, which is like the hardware store of data science and machine learning tools. So it all starts on the base. We've got your computer here. We're going to install Anaconda. And then once you've got Anaconda, getting all of these other machine learning tools like Jupyter Notebooks, PyTorch, Numpy, MatPlotLib, Pandas, Scikit-Learn, CatBoost, XGBoost, and TensorFlow. Whew, some of these are a mouthful, but once you've got Anaconda, getting these tools that we need to apply to that process we've just created, that framework we've created, will be an absolute breeze. So you've probably got this at the moment, your computer. Next, we'll have a detailed section on most of these, each of these, because there's a lot of machine learning tools out there, but I want to make sure that you've got hands-on knowledge with some practical ones that you can get started using straight away. And so what will this look like if we wanted to attach it to our process? Well, to write Python code and communicating our work, we're going to be using Jupyter Notebooks. And these are also the same kind of file you'll find all of the projects are done in. If you stick with it, you're going to finish the course with a few of these containing real-world machine learning projects where you can show people what you've done. And for data analysis, so this little section here, and we've done some color coding here on this diagram. So we've got this whole thing here, this whole modeling section of problem definition, experiments, and data analysis and machine learning. That can be thought of as data science. We've seen a similar graphic to this in the past, but this is now mapping the tools, which are these, to our framework that we've designed before. So for data analysis, you'll be using things like Pandas, MatPlotLib, and Numpy. That's step 2, 3, and 4. Building machine learning models, you'll use things like TensorFlow, PyTorch, Scikit-Learn, XGBoost, and CatBoost. And what's important to remember is your most important role will not be knowing all of the functions of each of these single libraries off by heart. It will be knowing which tool to use for what kind of problem. Again, that's why step one is defining our problem. So you can know, I can draw out of my tool bag here, which is this. I can apply these tools for these steps and these tools for these steps, and it's going to be all done in Anaconda and Jupyter notebooks. Sometimes you won't know the answer. Sometimes I don't even know the answer. But since I've had some practice, I know where to look. I've kind of thought about these different things. I've had hands-on practice with these different things, so I know where to come to look. And eventually you will too. That's what we're focused on. Okay, that's enough. You should be proud. You've learned some of the most fundamental concepts in machine learning. Of course, there are many more, and there's different ways to do the same thing. But these are more than enough, what we've covered so far, to start becoming a machine learning practitioner. Up next, we're going to get Anaconda installed on your computer. Because if we look at the diagram before, everything starts with Anaconda. Once you have your computer, you install Anaconda, you get these tools. So that's what we're going to do next. Let's do it.